Hello, my name is Jocelyn Bello. I'm from Group 4 and I'm going to talk about methane combustion process in air as a consequence of natural gas leaks in pipelines. The objective of our project is to find the composition of methane at a certain height where there is an emission source to determine if mixing with air will cause an explosion. For our project, we chose the Southern California Gas Company, SoCal Gas, which is a North American public company in charge to distributing natural gas, which is mainly made up of methane. The company used pipes installed 60 centimeters below the surface to distribute the houses and buildings, keeping them at the deep in case of leaks. Studies carried out by the company show that uncontrolled excavations are frequently carried out in which constructors are unaware that there are pipelines below the city, causing ruptures in the pipes. So natural gas doesn't have maximum limit allowed because it's not toxic. However, it's highly flammable at room temperature. Therefore, if there's a nearby flash point, the chances of explosion accidents are very high. For methane gas to produce an explosion in the presence of an emission source, it must be in a composition between 4.5 and 15% in a mixture with air. This produces a homogeneous reaction of complete first-order combustion, producing carbon dioxide and water. So the aim is to find the composition of methane at 2 meters where there is an emission source to determine if there will be an explosion, proposing a mathematical model represented as a concentration and composition profile. For this, the following assumptions. First, unidirectional diffusion of rectangular coordinates. Second, stationary system. Third, there is only diffusion of methane air. Fourth, the speed of the medium is neglected. Fifth, there is chemical reaction. For this system, the boundary conditions are at infinite height, the composition of methane will be zero, and at the beginning of the leak will be the molar flow. The transfer coefficient between methane and air was determined by biographic source, giving 2.12 square meters per second. After solving the differential equation, we obtain the concentration profile that is in a second row. Replacing, we obtain the composition profile, and evaluating the 2 meters at the results was almost zero for the composition and concentration. The graph on the right was made to predict how the methane composition changed in a range of height. The following graphs represent the first parametric analysis in which the temperature was varied with respect to the methane composition and the height. For the second parametric study, the pressure is varied with respect to the methane composition and also with the height. Composition profile presented an inverse relationship between the variables, so as the height increases, the composition tends to zero, since when it was evaluated at 2 meters, the composition was almost zero. In the first parametric study, the temperature increases, while the composition decreases. This is because the flash point of methane is 85 Kelvin, so at the room temperature, the gas is always flammable. The relationship between height and temperature is directly proportional. That means at infinity height, there will be no presence of methane because the combustion has been complete. For the parametric study of pressure, there is an inverse relationship for pressure greater than 5 atmospheres that composition will tend to zero. A directly proportional relationship between height and pressure was observed, giving a possible error because the parametric study is based on the composition profile and they maintain an inverse relationship. Okay, and finally, as a conclusion, the 2 meters were evaluated in concentration and composition profiles, obtaining values of zero. That's it. When height from the surface where the leak increases, the concentration and composition of the methane will decreases. Therefore, it's a conclusion that the explosion will have a low probability of happening and the leak can be controlled without any problem. That's good. Okay, and we have the reference. So thank you so much.